Welcome, everyone. I'm Julia Vogt. I'm professor at the Department of Computer Science at ETH Zurich. I'm leading the Medical Data Science group, and I will talk about machine learning for personalized medicine in pediatrics today. So first of all, the overall aim of my group's research is to develop new machine learning methods and decision support tools to solve open problems in precision medicine and in clinical data analysis. The fields medicine and machine learning are on a first glance two non-intersecting areas. However, they perfectly complement each other. And to close the gap, interdisciplinary collaborations are crucial. Now, why are interdisciplinary collaborations so crucial in this area? On the one hand, we have the researchers in machine learning, and on the other hand, we have the researchers in medicine. Now, the background of machine learning researchers usually is in computer science, in mathematics, or in physics. And researchers with this background can develop mathematically sound, beautiful models that are fast, that can solve problems efficiently. However, they're not producing medical data. And this means often they don't know the clinical problems and questions very well. Now, if a machine learning researcher develops a method to solve a clinical problem without having a clinician as a collaborator, this might lead to methods that are not applicable to real clinical problems. The clinicians, on the other hand, have a background in physics, in medicine or in biology, and they produce the data themselves. They know the clinical problems and questions very well. Often they can apply some machine learning methods by themselves. There are tools that allow that, where you can use machine learning without having a background in computer science. However, if you don't know the underlying assumptions of the models, this might lead that the models overfit or that the models are not fulfilling the underlying statistical assumptions, so that the results cannot be trusted. So, however, both fields perfectly complement each other, and bridging the gap between these two areas is crucial to achieve the joint aim of benefiting the patient in the end. So why do we need machine learning in medicine at all? In the last year, enormous progress has been made to gather as much information as possible about an individual patient, both on the molecular level, like for example, gene activity or mutations, as well as on the clinical level, like for example, patient treatment history. And also, hospitals see thousands of patients a year. Now, the medical data we obtain is highly heterogeneous. Here is the examples of blood values of kids with suspected tuberculosis. Here you see a PET-CT image of lung cancer patients. We obtain genetic data. Here you see an image of an ultrasound, image of a newborn baby heart. Here you see an example of a clinical text report. We obtain data from wearables, and we also obtain structured clinical lab reports. So the medical data we obtain is highly heterogeneous. It often contains a time component. Often we have missing data. We have imaging data, diagnostic data, data from wearables, and so on. So this is where machine learning comes in, because machine learning is able to cope with huge heterogeneous amounts of data that a single human or even multiple humans cannot process anymore, to learn from the data and to get a comprehensive picture of the patient. So the clinicians need support, and this is where we step in. And also these rich data sources present opportunities to develop and apply machine learning methods to enable personalized medicine or precision medicine. So to achieve the aim of patient care at the end, collaborative steps, as I mentioned, are really important. And to close the loop from the patient to the patient, this is the pipeline, how I think this can work. All starts with the patient visit in the hospital, with the generation of data. This also happens in the hospital. And then comes the data management step, which ideally happens already in close collaboration between the hospital and the researchers who would like to work on this data. Because data sharing and data availability is essential. If we cannot access the data, we will not be able to solve any problems. The data needs to be accessible technically, and legally. And these are two pairs of shoes. Both requirements need to be fulfilled for us to be successful. And after the data management step comes the machine learning step. This is where the expertise of me and my group lies, where we develop new machine learning methods for this specific data that arises in the medical domain. And then we again reach a collaborative step where we again meet with the physicians, discuss our results, discuss treatment decisions, and then it goes back to the patient. Now, today I will specifically talk about machine learning in pediatrics. Now, what is specific to pediatric patients? One point that is important that one needs to keep in mind dealing with pediatric data is that the dynamic is a lot different to the dynamic in adult data. Because kids grow fast, especially for newborns. In the first weeks and month, everything changes. The digestion changes, the weight changes, blood values changes. So what is normal in the first week of life might be completely abnormal in the fourth week of life, for example. So the dynamics is completely different. Also, one cannot easily do as many tests as one would like to compared to adults, because one has to consider many things that do not need to be considered in adults. For example, preterm babies have a blood volume of a teacup. So you cannot just draw blood as often as you would like to. So these are all things one needs to keep in mind. And another example is performing an ultrasound, for example, of their heart, and analyzing it is a lot more challenging than in adults. It is, for example, due to the fact that babies cry, they move, and if they cry out loud, that changes the heartbeat, they do not lie still. And also the normal shape and function of the heart looks different for babies at different ages. So the first week, it looks completely different than after 3 months. Another example, markers that are predictive for tuberculosis, for example, in adults are not predictive for children. So we cannot just transfer the knowledge we know from adult diseases to kids' diseases. And the same holds true for diabetes. The metabolism in kids is a lot different than to adults. We cannot just use the research results one obtains at adult diabetes to kids' diabetes. So in the last years, I have been mainly working in the domain of childcare and neonatology. And even if I focus on this clinical domain, there's still a wide range of application scenarios. And in this talk, I will concentrate on two specific projects I've been working on. One is about predicting severe jaundice in neonates. This is in the area of supervised machine learning. It is in collaboration with the Children's Hospital in Basel. And the second project I will talk about in more detail is about structure detection in newborn hearts. And this is in collaboration with the Kuno Clinic in Regensburg. So first, I will talk about the personalized prediction in neonates with machine learning. And this project is about detecting severe jaundice in newborns. So why is this important? Jaundice is one of the most prevalent medical conditions in neonates. Almost 60% of babies develop jaundice, and 10% of these babies need the treatment, which is phototherapy. Phototherapy means the babies are placed under fluorescent light, as you see here. And this treatment is non-invasive. This means if the disease is detected, it's treated easily. And usually if the child is in a hospital, the disease is detected because doctors are trained to detect this disease. However, if severe jaundice is not detected, this can cause major disabilities with lifelong consequences. And one of the aims of this project was to develop a tool that can detect early the risk of a baby to develop this disease, because the tendency is that mothers and their children are sent home earlier and earlier from the hospital, sometimes on the same day of giving birth. And the fear is that we send the mother and a kid home, and then the baby develops this disease at home, and at home it is not detected, and this should be avoided. So currently, the assessment of severe jaundice is based on our specific nomograms. And these methods provide a guideline for assessment. However, they are overly general and clinical performance is standardized, but it's not very personalized. So to achieve the aim of predicting the risk of a baby to develop jaundice early, we analyzed neonates in the first week of life. We had up to 44 patient characteristics available, which are, for example, demographics of the neonate and the mother, lab values, feeding information. We had all information about rhesus factor of mother and child, blood group of mother and child, and so on. These were 44 features. The data was collected in the first week of life, so it's longitudinal data. We have missing values, irregular spacing, so these are all challenges that arise in this project. The aim is to predict very early the risk of a baby that it develops this disease. The prediction should be personalized based on the characteristic of every single baby. And it should be a safeguard against too early discharge so that we are not sending a baby home that has an increased risk of developing severe jaundice. And it should be easy to use. So to achieve this, we developed a new classification tool, which is based on decision trees, which yields a very high accuracy in prediction for the need of phototherapy. And in addition, we performed a feature selection step. So we found out that it is sufficient to use the 4 main predictive features for prediction to obtain a very high accuracy. And this is important because it makes a tool a lot more usable. So we developed a tool here that can be used in the clinic on a daily basis. And here you see a screenshot of this tool. So what is needed is the physician needs to type in these 4 variables here, which are the four most important variables that already yield a very high prediction accuracy, then presses predict, and then gets probability that this child, where we just entered the variables, has an increased risk of developing severe jaundice in the next 2 days. And this variable selection step is very important because instead of typing in all 44 variables, which would be very time consuming, and so the tool would not be usable for physicians, is very important. So only typing in these 4 variables is doable. So here we developed a new machine learning model for the personalized prediction of severe jaundice. It yields an early prediction up to 2 days in advance with a very high prediction performance based on 4 variables. And although this tool is already very useful, we plan to extend the model even further. For example, we would like to extend the model to different phototherapy guidelines. Right now, it's based on the guidelines at the Children's Hospital in Basel. And also, we would like to extend the model to more diverse populations. We collected data, for example, from Germany, from Greece, and from China. And now we plan to develop a model that is general across diverse populations, so it can be used worldwide. Also, in addition to just predicting the risk a baby of developing the disease, we would also like to predict the duration and the intensity of the treatment. And last but not least, we would like to perform a prospective study with midwives so that midwives at home can perform this test. And if a baby has an increased risk, they can send it back to the hospital. So now I come to the second example. This is in collaboration with the Kuno Clinic in Regensburg. And here we analyze heart ultrasound videos of newborn babies. So here you see an example of a heart ultrasound video of a newborn baby. These videos are obtained in up to 5 different angles. So this is an exemplary view of where the ultrasound head lies. And then we get this video of the heart in 5 different views. So what's the aim here? we perform unsupervised structure detection and clustering, where we would like to incorporate prior information. Because often we have some domain knowledge. So for example, if we obtain these videos, some of them might contain the label which view it is from, but some might not. And in order to cluster these videos into similar groups, we would like to take the information we have into account to improve our clustering result. So we'd like to encode the prior information in the form of constraint into a clustering model. So you can do this in form of labels. So if we have the labels for every view, we can incorporate the labels. However, one of the most used type of constraints in clustering is pairwise constraints, which allow the user to drive the clustering algorithm by indicating which pairs should belong to the same class and which should not. For example, here, the first two pairs differ according to the domain knowledge, and hence they are connected by a cannot link that indicate they should not belong to the same cluster. And here the third example is with a must link, so it should belong to the same cluster. And it's important to know that it is always possible to go from labels to pairwise constraints, but not vice versa, as here we have less information. But usually obtaining pairwise constraints requires less effort to collect, as it is easier to compare than to classify. So here we developed a model that can take these pairwise constraints into account and also uncertainty. We need a model that can take uncertainty into account, because if we consider domain knowledge, we also need to be aware that mistakes might happen. So if you, for example, consider these views here, then we have physicians who label our data in must links, cannot links, constraints. So here we have for exemplary physicians, they say these two videos belong together. Those is a cannot link constraint, this is a must link constraint, and so on. And some of these physicians might not make mistakes in the labeling, but some might do some constraints. So some might make some mistakes. So we need a model that can deal with uncertainty. We cannot assume that all information we have is completely correct. And here we developed a deep clustering model that can deal with prior knowledge and with uncertainty. And we compared it to a state-of-the-art deep clustering approach. And here you see the state-of-the-art clustering approach. This is a PCA embedding of the latent space of the videos. And here you see that the results are quite discouraging. The clustering method cannot find the partition of the data that we are looking for. And here you see the result of our new clustering model, where we take the pairwise constraints and the uncertainty into account. And here you see in the PCA plot of the latent embedding that these groups are quite nicely separated. So these are just two examples of work that is important in pediatric medicine. And pediatric medicine and machine learning are on a first glance two non-intersecting areas. However, they perfectly complement each other. And to close the gap, to allow interdisciplinary research, mutual understanding, and a common language is needed. Now, I'm very happy to contribute at the intersection of computer science and medicine by developing new machine learning methods and tools that are tailored towards medical applications. And now I would like to thank you for your attention, and I would like to thank my collaborators and my group that work together to close the gap between these two disciplines. Thank you very much.